Hi, in the last chapter we are going to talk about the maximum flow problem. So let's get started. What is the maximum flow problem? There are several problems out there that can be reduced to the problem of maximum flow and minimum cut. Here are some problems. For example, a communication network has a set of requests to transmit messages between servers that are connected by channels, for example wires, that are capable of transferring information at varying rates. What is the maximum rate at which information can be transferred between two specified servers in the network? If there are costs associated with the channels, what is the cheapest way to send the information at a given rate that is less than the maximum? These questions can be answered with the help of the following Ford-Fulkerson or Edmonds-Karp algorithms. So I think it is definitely worth getting familiar with these problems to be able to decide later on what algorithms to use. Another problem has to do something with city government. A city government needs to formulate a plan for evacuating people from the city in an emergency. What's the minimum amount of time that it would take to evacuate the city if suppose that we can control traffic flow so as to realize the minimum? Traffic planners also might formulate questions like this when deciding which new roads, bridges, or tunnels might alleviate rush hour or vacation weekend traffic problems. So I think it's a very interesting problem. Another two problems. The first problem is the so-called and famous bipartite matching problem. We have 6 students, each needing jobs, and 6 companies, each needing to hire a student. These two lists give a list of job offers, which indicate mutual interest in matching students and jobs. Is there some way to match students to jobs so that every job is filled and every student gets a job? It is called a perfect match. And if not, what's the maximum number of jobs that can be filled? This problem can be solved easily with the Ford-Fulkerson algorithm. And the last problem is a given road connecting an army supply depot at the top to the troops at the bottom. And there are black dots, for example. It's a map, represents the enemy bombing plan that would separate troops from supplies. The enemy's goal is to minimize the cost of bombing, perhaps assuming that the cost of cutting an edge is proportional to its width. And the army's goal is to design its road network to maximize the enemy's minimum cost. I think it's very interesting problem too. So in these problems we have a directed a graph with directed edges, of course, and the edge weights are positive. These weights represent the capacity of a given edge. And we will have two parameters, the capacity of an edge and the flow. And the flow has to be positive and less than the capacity. It has to satisfy the local equilibrium principle. In physics it is called the continuity equation, so that the inflow must equal to the outflow for every vertex, except for the S source and the T sink or target. The value of the flow is the inflow at sink T. We can assign an F flow to each vertex. The flow is always equal or smaller than the capacity, as I said earlier, but it's very important. The directed graph has an S source and a T target. An ST cut is a partition of the vertices into two disjoint sets with S in one set A and T in the other side set B. The capacity of the cut is the sum of the capacities of edges from A to B. There are lots of cuts in a given graph. We usually want to find the minimum. It is the purpose of this algorithm usually, and it's a very famous theorem that the minimum cut is equal to the maximum flow. We are going to see it on the illustration. Yes, so the Ford-Fulkerson algorithm, we must construct the so-called residual network or residual graph. For every edge uv from u to v where the f flow is greater than 0, we direct an edge from v to u with residual capacity f. It is called a backward edge. For every edge uv from u to v where the f flow is less than the c capacity, we put a forward edge from u to v with capacity f minus c. When we will implement this algorithm, we will have methods in the edge class, and we are going to implement it. It's not so hard, but we have to remember these backward edges and forward edges. And we have to find an augmenting path in the residual network with the help of breadth-first search or depth-first search. Avant-garde algorithm uses breadth-first search, so we will do the same. So we put as much flow as we can through the augmenting path. We add the additional flow to the forward edge and subtract it from the backward edge. It will be important too during implementation. We will see it. We continue the algorithm until we find all augmenting paths updating edge flows on each iteration. So we will have a while loop that's going to run the algorithm as far as there is any augmenting path left. So for example, in this situation, we have a graph with directed edges, and the edges has two parameters, as I said earlier. 0, for example, the edge from S to vertex 1, there's a 0/10. The 0 represents the flow, and the number after the slash, the 10, represents the capacity. And as I said earlier, it's very, very important that the flow couldn't exceed the capacity. So the algorithm tries to find all the augmenting paths. For example, here's an augmenting path. We calculate the bottleneck. It is the minimum capacity of the edges that are in the shortest path from S to T. For example, in this situation, there are 3 edges, and we have to find the minimum. It is the 10. And we flow this unit through the network, so we update the edges. We find another one. Here's another augmenting path. We have to find a bottleneck, which will be 10. Yes, and we flow this 10 unit. There's another augmenting path. It's very, very important because there's a backward edge. For example, if we go from S to 3, then from vertex 3 to vertex 4, then from vertex 4 to vertex 1, we go back from an edge, so we will have to not to add the capacity to the flow, but to subtract it. So we find the bottleneck capacity, which will be 5, and we add to the forward edges and subtract it from the backward edges. This is the fourth Fulkerson algorithm. We have to do it. And we have to find another augmenting path. And the bottleneck capacity was 3, so we flow these 3 units of oil or water or whatever through this network, and no more augmenting paths left. So the maximum flow is 10 plus 10 plus 8, because we have to add up the edges that go to the vertex T, and we have to adapt the flows. So on the first edge, from vertex 2 to vertex T, the flow is 8. From vertex 4 to vertex T, the flow is 10. And from vertex 6 to vertex T, the flow is 10. So we have to add these numbers up, and it will give 28. Yes, finding minimum cut. We start from S and go until all edges are full. So starting from S, we cannot go to vertex 1 because it's full, 10/10. We cannot go to vertex 3 because it's full too, 5/5. We can go to vertex 5, so this vertex 5 is in the minimum cut set. Then we can go to from vertex 5 to vertex 6 because it's 13/16. We can flow another 3 units. So it's okay. Then we cannot go from vertex 6 to vertex T because it's 10/10, but we can go from vertex 6 to vertex 3 because it's 3/6. So, but from vertex 3 we cannot go anywhere. So these 4 vertices are in the minimum cut: S, vertex 3, vertex 5, and vertex 6. Yeah, we are going to implement it in the next video, and it will be clear. Thanks for watching.